The broadcast is now starting. All attendees are in listen-only mode.
Hello, we want to welcome everyone to another edition of TruTech Training, TruTech Webinars. This webinar does have BPI-CEUs attached to it. If you've sent us your BPI certificate number when you registered, we will put in within the next day or so, we will upload the 1 CEU credit if you've paid attention through the whole webinar. And we have ways of telling these things. So I want to welcome Steve Rogers of the Energy Conservatory.
Thanks, Bill. It's great to be here.
Great. So we're going to be talking about how accurate is your airflow capture hood measurement. This should be very interesting. We are recording this session. So if you want to go back and look at it again, it will be on the TruTech YouTube channel. Or if you want to tell somebody who missed it, give us like a day and we'll have it up there as one of our recent uploads about this exact session that you're watching right now. So I'm going to turn it over to Steve. I think you have the screen already.
Yep, I hope everyone can see my screen. This, just so everybody knows, this is a presentation that I gave at ASHRAE last year as part of the Instruments and Measures committee that I serve on. And I'll just get started here. So let's see, oh, that's not working. Okay, so first I want to give some background, a little bit of characteristics of air balancing measurements in HVAC applications, because many of the products that are out there are focused on commercial, and residential is really a little bit of a different animal. I want to talk about an example that illustrates the need for measuring and balancing even in residential applications. And then I'm going to explain the test setup that we used to evaluate flow hoods. And I'm going to explain each of the hoods, the supply registers, and orientations that we tested. I'll show the results of our tests and then explain conclusions from the test data and from the example that we used. So if we look at residential flow hoods, or residential flow hood applications rather, they're smaller in size, lower flow than commercial hoods. Many of you are probably familiar with the 2 foot by 2 foot standard commercial supply register that's on typically on a drop ceiling application, and residential is smaller and lower flow. There's probably an even wider variety of diffusers used in residential applications, and there's some real significant accessibility challenges in actually trying to get the hood onto the register. This is a photo of one that's right between a toilet and a wall, so real challenge to get a flow hood on that one. It's not uncommon to have the supply register in a crown molding, to have it in a toe kick. These present real challenges. They're not insurmountable, but if you want to know how much flow is coming out of there, you're gonna have to do a little extra work. So probably most of us know that in residential applications, supply registers are very seldom measured and balanced. And I want to ask, why is that? I think there's a widespread perception it's not really necessary, that the tools are too expensive, that many of the tools are indeed designed for a 24 by 24 inch commercial diffuser. And some registers are impossible, in quotes, to measure. We've found ways to measure them. It just takes a little diligence and a little effort to do that. So is there really a need to measure and balance in residential applications is the question. And to answer that question, we're going to ask the Jones family. This is a real life case study that's here in Minneapolis. Hang on, pardon my phone. Okay, so this is the Jones home near Minneapolis, Minnesota. It's a 2-story colonial. It's about 3,100 square feet. There's probably nothing really unique about this home. The basement is mostly finished and conditioned, and that will come into play as we look at the measurements that we took on this house. The walls are well insulated, and as is the attic. It's 2x6 construction, good air tightness, 2.4 ACH50. But the family that lives there has comfort complaints. They tell us the master suite is under-conditioned and the west bedrooms are over-conditioned. So we wanted to address that. And now here, this maybe is the most important bullet. They tell us all their neighbors have similar comfort complaints. And I don't know about those of you who work in the industry, but every time I tell people that I work in anything related to HVAC, they start telling me about their comfort complaints. And so it's not, I don't think that this experience is unique really at all. You'll find that there's part of it that's unique, but on the whole, it's really not. Okay, so as found, this is what we measured. The air handler total flow was 536 CFM, and the static pressure in the supply plenum was 0.53 inches of water column. And the air handler is located down here. Can you see my pointer?
Yes, you can see it moving around. It's tiny, but
Okay.
I can see it. Yeah.
Yep. Okay. So the air handler was located in one end of the house, which means there was a main supply duct that goes, down the center of the house on the basement level, and then there were branches that go around the main level and up to the second level. And in the title here, it says, as found, main damper closed. And the reason for that is we actually found that there was a main damper between the air handler and the main trunk duct that was completely closed. And so as I show the flows that we measured here, you'll quickly discover where each of these branches was located in relation to that damper. So we measured 9 CFM in the dining room, 6 CFM in the kitchen, and the dots here are scaled to represent the amount of flow. 4 in the family room, 6 in the other one in the family room, 9 in the kitchen, or we're in the living room now. And then 144 CFM coming out of one supply register in the living room. So it was a similar story upstairs. You can see the entire master bedroom with its master bath and walk-in closet had a total of 8 CFM, while each of the 2 bedrooms had over 100. So it's not hard to figure out which of these 3 branches come off upstream of that damper that was closed, and everything else, there's almost nothing coming out. And in total, we had about 187 CFM going to the main floor and about 240 on the second floor, because of course 2 of those that were getting a lot of flow were upstairs. But it's important to point out this was an error. That damper should not have been closed, and we don't know at what point it was made and how long, but the family has never had adequate conditioning, or had never had adequate conditioning in the master bedroom, and it was always over conditioned in the upstairs bedrooms in the other end of the house. So the first thing we did was open that main damper, and we remeasured everything. So by opening that damper, we got 15% more flow. We're up to 620 CFM nearly, and the static pressure dropped to less than 1/5 of what we had measured before. There's only 1/10 of an inch of water column in the main supply plenum coming out of the air handler. So we started measuring, and here's what we found after opening that main damper. So you can see it's significantly better. But now we've got a slightly different problem, and that is we've got a lot of flow on the main floor and probably not enough on the second floor, especially in the air conditioning season. Because remember, this is a basement, main level, and second story. So the main floor has conditioned space above and below it. So you probably don't need that much, or in proportion to the second floor. So the Jones family reports that comfort is improved. They're more comfortable in the master bedroom, but it's still not well balanced. And now we've eliminated this erroneous situation where the main damper was closed. This is how the home was designed, and this is how it was built. That main damper is now completely open. But as you can see, we've still got about, just about 50 CFM in the master bedroom, and each of these end bedrooms, we've got nearly 100 CFM in these two bedrooms, which occupy about the same floor space and about the same number of exterior walls and windows as the master suite does. So they're still not comfortable. And this is exactly how the house was designed and built. So we set out to do a little bit of balancing. And I should say that we didn't actually do a manual J on this house. We just sort of looked at the results and said, well, we know you need more, or we know where you need less flow. And I think we only adjusted 3 or 4 dampers, and they were the 3 and the 4 that were getting the most flow, and we closed them significantly. So after doing that, these are the results that we got. And you can see it's much better balanced. I would say it's not perfect, but it's doing better. And now you've got about the same amount of flow on the main floor as you do on the second floor, which is adequate for heating season, but probably going to be a little warm upstairs in the cooling season. But the Jones family reports that this is a significant improvement in comfort and that it was very well balanced. And just to emphasize their happiness with the comfort, when we first started talking with them, the couple in the master suite reported that ever since they had purchased the house like 8 years before, they always slept with the electric blanket in the master bedroom all winter long. And so when we started balancing, I told them, you're probably not going to need that if we do a decent job with the balancing. And they were skeptical and said, no, we kind of like our electric blanket. We don't think you're going to get it that comfortable. So after we had done a little bit of balancing, I got a text from the owner of the home who told me, well, you're right. Last night was a good cold night. We started up the electric blanket, and then 10 minutes later, we turned it off because it was too warm in the master and too warm in the bed. So that illustrates that, they finally had achieved the comfort that they should have had all along.
Hey, Steve, someone asked the question,
Yep.
What was the tonnage on the furnace or AC for this home?
I don't recall the tonnage on the home.
Okay.
In fact, I didn't look at the air handler either. That if you look at the flow, it seems kind of small, but this is, the footprint of the home is not really that big. So this could be, it might even be a 40,000 BTU furnace, which for a well-insulated, fairly modern house is probably significant even in Minneapolis.
Got it. Thank you.
It's probably sufficient. Okay, so that illustrates the need for doing residential balancing. Now let's look at the tools. What do you need in a flow hood to get the job done? Well, you need accuracy, and we want to talk about insertion loss as well. This is a term that maybe you're not that familiar with, but I'll illustrate it with an example, and we'll hopefully it'll make sense to you. So I think most of us have a pretty good kind of intuitive understanding what accuracy means. This is a definition that shows up in a JCGM standard that's used for uncertainty analysis. And you can read it, but in a sense, it means how close is it to the true value. Insertion loss is a little more difficult to understand. I found only one definition for what insertion loss is, and it came from telecommunications. So we'll throw that out. It's not especially useful to our situation. So I cooked up my own definition of what insertion loss is, and that's when the change in the value of a physical parameter being measured, or it is the change in the value of a physical parameter being measured due to the insertion of the device used to measure it. So it's when the measuring tool changes the thing being measured. And the easiest way to understand this is with a barbecuing example or cooking example. Hopefully you like to cook. If you do a lot of cooking, you've probably used a meat thermometer, and maybe you have or haven't thought about the fact that when you put a meat thermometer that's at room temperature into a piece of meat, you want to measure the temperature that the meat was before the thermometer went in, but your thermometer actually cools the meat down a little bit because it's going in at 70 degrees Fahrenheit, and you're trying to measure a piece of meat that's at, maybe 140, 160. So how much does that cold thermometer cool down the meat? Well, if you put it into a 5-pound roast, it's going to be almost nothing because the thermal mass of that probe is pretty small compared to a 5-pound roast. But what if you put that same stainless steel probe into a 4-ounce hamburger patty? How much are you going to cool down that patty, and is that going to affect the measurement that you're trying to make? So now let's take that to an extreme, and let's say, okay, now let's assume in the first place that you could slice a slice of bacon so thinly that you could actually get the probe inside it. But even if you could do that, you couldn't measure the temperature of that bacon because the thermal mass of that stainless steel probe is probably larger than the thermal mass of the bacon. It's going to cool down the bacon more than the bacon's going to heat up the probe. So you're not going to get a measurement that you wanted, which is how hot was the bacon before I put the probe in. You're going to get an average temperature of the probe and the bacon. So if we take that example and look at flow hoods, the question is, how much does a flow hood change the flow that you're trying to measure? So you can think about this in terms of resistance to flow, or it adds back pressure. Many hoods add a little bit of back pressure, and that affects the flow. So we set out to measure with this laboratory both the accuracy of the flow hood and its insertion loss. So what we have here is a setup in our laboratory that is driven by a flow metering fan that's calibrated to 1% of flow. So this fan is also, it's being controlled so that it maintains a constant total flow. So it's like an ECM motor, and it's actually probably slightly better than an ECM motor because most of them have a slight drop off with increasing pressure. This system is able to maintain exactly the same flow regardless of the back pressure. We had 4 interchangeable supply registers in each of these platforms, so we can swap them around and easily measure different styles. And then each branch has an iris damper / orifice meter, which is calibrated to 2% against this flow metering fan. So we can seal off each of, or 3 of the branches, and then the one that remains, we can compare the flow through the fan to the orifice, and we know that each of the orifices is capable of measuring within about 2% how much flow goes down each branch. So we also, of course, need to make sure the total system leakage is very low. We had less than 1 CFM total system leakage with a pressure of 0.2 inches of water column in the main trunk. So we've got a data acquisition computer that's monitoring each of the branches and the total flow through the fan that represents the air handler. Okay, we evaluated 6 different hoods. Maybe you recognize them in conformance with ASHRAE standards. They're not identified other than by their characteristics. So hood A was a standard 24-inch by 24-inch hood intended really for commercial measurements, and the flow is measured with a pitot array. It's a passive hood, meaning it doesn't have a powered fan in it to compensate for the back pressure difference. Hood B is a rotating vane anemometer that's attached to a 13 by 13 inch funnel or capture hood. Hood C is a smaller size 16 by 16 inch that uses a hot wire anemometer array for the flow measurement. It's also a passive hood. Hoods D and E are both powered flow hoods, with Hood D using a pitot array for the flow measurement, and Hood E uses the RPM of the fan to measure the airflow. Hood F is a 24 inch by 24 inch hood, and it uses a rotating vane anemometer, and it's also a passive hood. So that's what was evaluated, and each of these hoods was measured on 4 different supply registers. We've got a 4 by 12 inch that's got a two-way throw. It throws right and left. We've got a 4 by 12 inch that throws three-way, right, left, and up. We've got a 2 by 12 inch. These are real common in the Midwest in bathrooms or toe kicks. And we also used a 2-inch jet. These are probably less common, but they're becoming more common in very energy efficient houses where you just don't need a lot of airflow. Okay, so 6 hoods, 4 supply registers, and 6 orientations of hoods on the register. So each of the symbols that you'll see, we've got the box and the star and the X, triangle and the diamond and the plus sign. Each of those represents a different orientation of the hood on the supply register. And we've got those kind of grouped together. You'll see how much the flow measurement changes or how much the error changes as the hood is moved around on the register. Okay. So these are the results from the 4 by 12 inch two-way throw that's measuring 100 CFM. So let me tell you how to read the graph here. The first thing to know is that this is at 100 CFM. So before we put the hood on, the branch was flowing 100 CFM, and we know that from the orifice that's in the branch. So in the horizontal axis, this is measuring insertion loss. So you can see 100 CFM is this line here. And so any flow that's less than that, it's because of the insertion loss of the hood. So you can see that, hood C has only about 3 CFM of insertion loss, 2 or 3. Hood B had a very large insertion loss. It dropped the flow from 100 CFM all the way down to 70. And in the vertical axis, this is accuracy. So you can see that the 0% is here. So for example, hood A consistently read way too high. Hood C is reading too low. And the red box represents 3% error, both in insertion loss, which is left and right, and in accuracy, which is up and down. So if a flow hood has both less than 3% insertion loss and less than 3% error, all the dots will be inside the red box. So you can see hood A is the 24 inch by 24 inch hood, and there's very little insertion loss, which makes sense because it's an enormous hood for residential applications. But the accuracy was way off, anywhere from 10% to almost 30% high. Hood B was that small anemometer on the rigid funnel, and not surprisingly, that's the smallest hood. And so it was reasonably accurate, better than 5% accuracy. The problem is you're trying to measure 100 CFM and it creates so much back pressure, it reduces the flow down to 70. So you're not going to know that there was 100 CFM on there before you put the hood on. Okay, so the results from the 4 by 12 inch three-way throw are very similar. not too much different there. Again, hood A, very little insertion loss. Hood B, huge insertion loss. So this is the 2-inch by 12-inch register, and this one we're flowing at 50 CFM, which would be, you know, much more realistic for a register of this size. And so a hood F requires a restriction plate, and it says that you're supposed to not use the restriction plate if the flow is higher than 50 CFM, and you are supposed to use the restriction plate if it's under 50 CFM according to the manufacturer's instructions. So right at 50, we tested it both ways, and you know, you're supposed to either use it or not use it, but you can imagine that if we had done this at 51 CFM and then done it again at 49 CFM, the results wouldn't be any different. So hood F with no plate had, you know, real accuracy problems depending on how you orient it on the supply register. It could be anywhere from 25% high to 15% low. With the plate on it, it's got difficulty with both accuracy and insertion loss. Now you're knocking down the flow from 50 down to, in most cases, under 40. Okay, so the 2-inch jet, I want to point out here that the accuracy scale is now way stretched out. In the previous ones, we were seeing, you know, minus 40 to plus 50%. With this jet, all the hoods did worse. So now we're looking at minus 100% to plus 250%. So hood A is that big 24-inch by 24-inch hood, and that reads anywhere from 50% high to over 200% high. So you're looking at reading more than double what the actual flow was. Hood B was the funnel. Again, here there's very little insertion loss. What's kind of strange is you actually get an insertion gain. So there was 50 CFM before we put the hood on, and when you add the hood, that might go up to almost 55 CFM. But yeah, so the 3% error box is way compressed down in the vertical direction because we stretched out this scale. So I would say none of the hoods did great. Probably none of them are within that 3% box, but obviously some do better than others. Okay. So the question comes up, do you need good accuracy and low insertion loss? Do you have to have both of those in a hood? Or could I pick a hood where maybe the accuracy is not great, but at least I'm not creating additional insertion loss, or vice versa? It's an accurate hood, but maybe it commonly creates a lot of insertion loss. To answer that question, we have to spend a little bit of time looking at what does accuracy depend on. It depends on which style of hood you have, depends on the position on the register, and it depends on the style of diffuser that you put it on. You know, whether it's the 4x12 or the 2x12 or the jet, you know, the 2-inch circular. And ask yourself, if I'm an HVAC technician, I'm trying to measure and balance a home, which of these three do I get to choose? Certainly you can choose which style of hood you buy, but in most cases you don't get to choose which position it is on the register because the register is up against a wall. Maybe you have some control over that, but you might have very little at all. And the style of the diffuser, that was chosen when the home was built or remodeled. So that's, you don't have any control over that. So if those things that you don't have control over affect the accuracy, then you can't really correct for it.
Hey, Steve.
Yeah.
At some point, the folks would like to see the visual of the different types of devices to correlate with the letters. So that would be a good thing.
Yeah. Do you want to roll back now?
Yeah. Why don't you do that? Because the question just came up.
Yeah. Okay, so here's the hoods again. Hood A is the biggest, hood B is the smallest. Hoods D and E, it's hoods D and E did the best, and it's not a coincidence that those were the two powered flow hoods. There's a reason why that is, which I can explain. And hood C was reasonably good, but not outstanding. Hood F was kind of in the middle. So we'll go through. I think maybe this one's maybe the most instructive because it's kind of where everybody had some trouble. So again, this is the big 24-inch by 24-inch. Hood E was the white powered flow hood. Hood D was the black powered flow hood. Those consistently did the best. Those are the two powered flow hoods. Hood C is that small size blue hood that has the hot wire anemometer array inside it. Hood F was the kind of gray rectangular hood with the vane anemometer mounted inside it. Hood B was the big 4-inch vane anemometer on the hard plastic funnel. And A is the big blue 24-inch by 24-inch with the anemometer, or with the pitot array for flow measurement. So does that help people get a little bit oriented with which hood is which? The pattern that you see is fairly consistent. B always had a big insertion loss. A always had a big error. D and E do the best. And C was pretty good. F was kind of sometimes okay, sometimes not.
We just sort of follow-up question there. Hood D is the powered flow hood by the Energy Conservatory. I think we can mention that, or I'm mentioning it. And people are asking, why is it so hard to find? I don't know if you want to get into that now, but I think that's an important thing on people's minds.
Yeah, so I'll go ahead and take that question now. So the Energy Conservatory's flow hood was discontinued about a year ago, and the difficulty with it, anybody who ever used one could tell you it was really accurate and also not especially easy to use. So, but the reason it was canceled had nothing to do with the measurement of the flow hood. It was the battery pack. We worked with a supplier to provide a battery pack, and it turns out that if you didn't charge the battery pack and let the flow hood sit for like 6 months or a year, which some of our customers did, the battery pack was irreparably destroyed and you had to replace the battery pack. That was not a good customer experience. It was not what we expect as a manufacturer of equipment. And so rather than, we also tried to see if we could retrofit a better battery pack, and it just wasn't feasible from the engineering review that we did. So I will say that we are working on a new flow hood that will be as accurate as the one that we've sold, and easier to use for sure. That's our objective, is to make it very convenient and simple to use.
One related question there: can you use the DG1000 on flow hood D?
Yes, you can. Oh no, wait. There, we don't have a mounting plate, number one, and I can't remember if it's even in the. I think the answer is no. I think you have to use the old DG700.
Got it. Thank you.
Okay. So stay tuned. Better things are coming. The other thing that I can tell you is that if you really have a need for a very accurate flow hood, call us and talk to us, because they can still be used by plugging them into the wall, which makes it a heavy, cumbersome hood even less convenient. But if you've got a real strong need and you're willing to do that, give us a call. We can still sell you one. But it'll be plugged into the wall rather than with the battery pack. Okay. So we talked about how accuracy depends on the style of the hood, the position on the register, and the style of the diffuser. Insertion loss is a little bit more complex to think about what affects the insertion loss. It turns out it's very highly dependent on the flow rate. If the flow rate is higher, you're going to get more insertion loss. If you've got, 10 CFM coming out of register, almost none of the flow hoods would have a significant insertion loss. So the higher the flow, the higher the insertion loss. The size and the style of the hood, mostly the size. If you look at those results, the smallest hood always had the largest insertion loss, and that enormous hood almost never had an insertion loss. And the powered flow hoods had very little insertion loss, which is one of the points of their design. They're designed to do that. But the insertion loss also depends on how much restriction you're adding, or the hood loss, relative to parallel paths. And what I mean by that is how much back pressure is the hood creating compared to the back pressure of the other 3 branches. So our setup had just 4 branches, but if you put the hood on it, you can see the flow in the other 3 increase. So the relative loss between the other 3 registers and the one that the hood's on, that affects your insertion loss. But it also matters how big the hood's loss is compared to all the other losses through the register grill, the branch, the trunk, and all the way back to the air handler. For example, if you've got undersized ductwork that has a really high loss, and you put the hood on a 4x12 inch at 100 CFM, it's not going to make a big difference, because most of the loss total is through the branches in the duct system. On the other hand, if you have a very oversized duct system, so there's not a lot of loss through that system, and you put the same hood on the same 4x12 inch grill at the same flow rate, it will create a larger insertion loss, because now the hood is significant compared to all the rest of the losses through that branch. So the bottom line is, yes, you need both good accuracy and low insertion loss to effectively balance an HVAC system. And Bill put this in different terms that I think are really good. Bill said, so there's no correction factor that can compensate for either type of error. And that's correct, because the correction factor would be different for every single grill that you're measuring. And so there is no correction factor that you can apply. So if you want to get good effective measurements, or to effectively balance the system, you've got to have good accuracy and low insertion loss. So what our data says in summary: accuracy errors of 15 to 50%, 50% were common, and in some cases over 100%. That standard 24 by 24 inch passive hood is really not suited for residential applications. It just doesn't work. And which makes sense, because it's not what it was designed for. Insertion loss errors of 30% in the case of that smallest hood. The orientation of the hood accounts for 15 to 20% variation, and that was quite common to see that. So the other interesting thing that I learned from Gary Nelson, the founder of our company, years ago, is he said, you can do a real easy field test if you want to get some idea how good a hood is. All you need to do is put the hood on a supply register that has, that you can easily access, and start moving the hood around. Put the supply register right in the corner of the hood, put it right smack in the middle of the hood, turn it 90 degrees and do that again. And you'll see that the more accurate hoods, that measurement won't change very much, a couple of percent. But the hoods that are less accurate also are the same hoods where, you know, you've got 20% variation when you move the hood around on the supply register. So there's a pretty good correlation between how accurate they are and how much they change when you move them around on the register. Okay, powered flow hoods were more accurate and have a smaller insertion loss. And it's not surprising that they have a smaller insertion loss. That makes total sense, right? That's what that fan is supposed to be doing. It's supposed to be compensating for the insertion loss. But it's not obvious why the powered flow hoods are also more accurate, but there is a reason for that. And the reason for that is that both of the powered flow hoods have something that none of the other hoods have. In addition to the fan, they also have a flow conditioner. If you look inside either one of those hoods, there's like a settling screen or a grill or a flow conditioner with holes punched in it. And those make the hoods more accurate. It's the flow conditioner. However, if you put a flow conditioner in a hood that doesn't have a fan in it, you're going to have way too much insertion loss. So that powered flow hood is actually doing two things. It's compensating for its own insertion loss, but it's also compensating for the insertion loss of the flow conditioner, and that's what makes them accurate. Okay, so what does it mean? Comfort problems abound in residential HVAC applications, and most of them are very difficult to diagnose if you don't know how much airflow is going to each supply register. I mean, you can wave your fingers around, but if you haven't made a measurement, you're just guessing. Balancing is easier and requires less precision in buildings that are better insulated and more airtight. So the reason I say this is a conclusion from our data, this is really from the test case. So the Jones home that we talked about was quite airtight, had 2x6 construction, and it was well insulated. If that home had been built in the 1950s and it had very little insulation in the walls and not much insulation in the attic, the comfort problems that they had would have been unbearable. There might have been frost in the master bedroom. But because it had a really good envelope, their comfort problems were tolerable. I mean, they had to get a electric blanket, but that's why I say that balancing is easier and requires less precision in buildings that are better insulated and more airtight. So the better the building, the easier it is to balance. So if you're working in older homes, less airtight homes, it's going to be harder. You have to get it closer in order to achieve the same comfort. And bottom line, many airflow hoods may not be accurate enough for applications that are more challenging to balance, and those would be poorly insulated, leaky envelopes, also, you know, complicated building structures. If you've got a big complicated house, it's going to be more challenging to get it properly balanced. You're going to need to do your manual J. You're going to need to make sure that you measure each branch if you want to achieve the same comfort.
So thank you, Steve. That was very informative. We had a couple more questions here, which I've been answering along the way. And one of them, which I gave the answer to, is how do you pick the best one? And my reply was, it depends on your budget and your required level of accuracy. What would you say to that?
I think that's exactly right. You know, a lot of people might guess that. You know, I think many of us know that almost all these are all these available from TruTech Tools.
Yes.
Bill?
Yes.
Yeah. And so you know, they know the price range, and you might guess that as the manufacturer of one of the better hoods, I might be real disparaging of the $400 hood, the cheapest one. And the fact is, I'm not that disparaging of it. And the reason why is because right now, nobody's doing any residential balancing. And if we want to achieve comfort and serve our customers better, we've got to start doing this. This is how you solve comfort problems, by knowing where the air is going. And so a $400 flow hood that's not very accurate is way better than waving your fingers over the grill. I promise.
So I liken it to a gateway drug.
Yeah. Yeah.
It's going to get you
now,
tested. Yeah.
Yeah. Now, after you've had that hood for a couple years and you notice that it changes a lot depending on whether you've got a grill in the corner or right in the middle, maybe later on you're going to say, I need something better. This just isn't good enough. And that's, where, I'm in favor of more measurements and understanding what's going on. And I realize that most people, if they don't have a flow hood, aren't going to start with the top of the line one. Maybe some people are just going to look at the information and say, I need the good one. And that's great. But yeah, I'm not disparaging of the cheapest hood, because what they're competing against is no hood.
So another question was, and I think there was actually a question stream from Jeremy that's come through, and this is sort of the last question. Will the 24 by 24 hood skirt, if you will, be okay to check the return CFM only? And I wanted to qualify that and say, if you're using a passive hood, the 24 by 24 skirt would have to fully cover the grill or the airflow path.
Yep.
However, and I wanted to check with you on this. If you're using a powered flow hood, you could test segments of the grill if your device skirt did not cover the whole grill. Is that true?
No, not really. I don't think the pressure balancing is good enough to put it on half the grill and get the right answer. We didn't do a lot, or we didn't do any measurements with return flows. I would check with manufacturers. The other thing that I would say, though, is that for total system flows, the TruFlow product is really the best and most accurate way to do those. The only challenge there is when you have a system with two returns that doesn't have a filter slot in a common part of the system.
Got it.
So then you end up with one TruFlow and one flow hood, or two TruFlows, or something like that.
Okay. And we have a few more questions here. I'm just going to continue through them, if that's okay.
Sure.
This one is, how is zonal pressure testing? How does it compare to flow balancing?
I'm not sure. I don't know that there's a big relationship between zonal pressure testing.
I would agree with you. I'd say they're two different purposes. Zonal pressure is to check for pressurization or depressurization of a zone or a room, and flow balancing is to check for air mixing and achieving comfort in the space. So two different objectives. They don't compare. It's like saying, how does balancing your tires do with cleaning your windshield?
Yeah, there might be one relationship, and that is that if you're measuring room-to-room pressures, it depends. If you're measuring room pressures that are caused by the air handler system, for example, if you don't have enough return path in a particular room, and so the particular room gets pressurized by 3 pascals, what you can do is you can flow hood test it if you've got a really accurate flow hood, and see, okay, well, when the door's open, the room-to-room pressure is 0, but when I close the door, it's up to 3 pascals, and how much is that reducing the flow from my supply register? So that's the only relationship I can see there. If you're looking for leaks in the building envelope by doing zonal pressure diagnostics, there's no relationship, like Bill says. But sometimes you're measuring room-to-room pressures just to find out if the HVAC system is pressurizing a room because there's not a good return path,
right?
Or because there's too much return from a room. Yeah,
I'd say it's more of an oblique diagnostic, not a real direct one.
Yeah.
Okay. Another question: are there any requirements for hoods? That is, do you need a powered one to complete balancing, or is it not regulated yet?
I think the answer is most of the country is not regulated. I was talking with an official in the state of Idaho at, I think it was the ResNet conference a year ago. And I think we're actually requiring a manual J and then requiring technicians to actually balance and show that they were getting the room flows required by the manual J on new construction, which I think is a good idea, but they don't have many comfort problems on those newer homes that did that.
Yeah, and I think you're aware of ANSI ResNet Standard 380, which talks more about ventilation airflow than actually room to room.
Yeah. So and flow hoods can be used to measure exhaust fan flows as well. So that's not balancing for comfort. That's verifying your ventilation flow. But that's another, and that is very often part of regulation.
Okay. And Gene asked, what equipment is recommended for those oddball grills? And I'm not sure exactly what he meant by that, but
okay. So yeah, the toe kick grill.
Okay.
It's basically you get out your cardboard and your tape. If anybody's interested, shoot me an email. I can show you the special cardboard flow hood adapter that I use to get that one between the toilet and the wall. With a toe kick, you can very often wrap a piece of cardboard up the front of the cabinet, tape it above the register, and then put foam on the left and right side under the toe kick. So yeah, you have to get creative, but the idea is to create a flat surface where the hood can seal and get that the flow so that it's all going through the hood. Yeah, cardboard and tape is your friend.
Yeah, and the other one of the training organizations that we've worked with talks about using fuzzy dice instead of foam, and that may echo in some people's minds, and others it might fly totally over their head.
Yeah.
Another question: where were the returns in this house? The example house.
The example house is a Minnesota house, so returns in every room.
Okay.
Almost every room. Sometimes you'll have a bathroom that has a supply and no return, but in Minnesota, the common practice is all the bedrooms and all the main living spaces have returns. Occasionally, kitchens and/or bathrooms won't, but the major rooms do.
Yeah. Okay. This is a good one from Mike. Have you guys considered creating a residential air balancing app that relies on data loggers placed in rooms to rebalance the system after you input current CFM, and the app calculates the recommended CFM not based on a model, but based on temperature?
I haven't considered doing it based on temperature, but certainly we've considered an app that you can compare it to manual J. But that's not a bad idea.
Okay. And Mike, you see Steve's email here, so if you want to follow up with Steve, you should do so. Another question. Okay, one was, I guess this is just a general question. Is it okay to use hood A as long as it fits over the return?
We didn't test hood A on returns. It
Okay.
may be fine for a return. In fact, returns, as long as the hood is capable of measuring that flow without too much pressure loss, returns tend to be easier because you're mostly taking still air from a room. And so there's, you don't have to worry about, is it blowing on the left side of the hood or the right side of the hood, which is where all these errors come from. Yeah, I can't, I'm going to guess that it's pretty decent on a return flow that's large. I don't think it's accurate at very low flows in general, but if you're measuring 500, 800 CFM with that big hood, it's probably pretty good. It's just a guess. We didn't test it.
Yeah, I think it is still air collection is what you're doing, and It's very lazy flow moving towards the device, the measurement device, and it's not as challenging as pressurized flow slamming it from all directions coming out of a grill.
Yep.
Okay. All right. I think that takes care of it. We had a good number of people that stayed throughout. There was up to a peak of 85. So I want to thank everyone for coming to this. I don't see any other questions coming in. We'll give a quick plug for TruTech tools here. I'm trying to look for a way to switch over the. Oh, the other question was
the only place you can get all those hoods, right?
Yeah, right, exactly. One of the other questions was, would you be willing to provide a PDF of the slides?
Yeah, we can do that.
Okay. And actually, you sent me one before. If you wish, I can if there's been no changes, I can just send that.
Yeah, I put a couple. I don't know if we have well, let's you and I coordinate afterwards. Okay. I think there's probably a couple more things.
Sure. So what I'll do is for the attendees, I will send you a link later on to a file location where you can download it. I won't email it to you, but I'll send you a link to download it. So one last thing, I'm just going to take over presentation control here for a second and just show you where you find these things on TruTech site. Maybe you have to turn it back over to me, Steve, in the control.
Okay. I can't figure out where to.
Under attendees, perhaps.
Yep. Okay. You should be presenter now.
Okay. So wanted to give people just a quick tour of what you're seeing here at TruTech Tools. We do have a section for airflow measurements and test and balance. So that's in the category tab here. So if you're looking for a specific way to do things, we also try to give you some instructional information here, and I'll send you to that, which talks about tips and techniques, which we've accumulated from our learning and also from the generous learning of our provided by our manufacturers in many cases. If you're also looking for a specific product, just type it into here. So like, for example, the Easy Hood, you see it actually fills in and does the drop down. You can just hit return and it'll collect and bring you to the different Easy Hoods that are available as an example. And the other thing is we do also have a live chat function for people that want to use that. It was a lot of times we have agents online who are right there live to answer your questions, or you can drop a line to start the chat if you want to start a conversation, say after hours or something like that. And also info@trutech.tools.com. We have a toll-free number, business hours, Monday through Friday. We're there, and we do free shipping on all orders to any U.S. state, Alaska and Hawaii included. Any order over $98 ships for free. So I want to thank you for listening to this session, and want to really thank Steve and all the folks at the Energy Conservatory sort of for their kindness and patience and diligence. I really think I'm going to embarrass you here, but you guys are really all about the industry. I just get that sense time after time after time again. It's not just the business; you guys are about the industry. So thank you.
Yeah, thanks very much. We're just trying to make it easier to measure what you need to measure.
There you go.
And I appreciate the time. We'll have to do it again.
Yeah, we will do it again. Thank you, Steve. Thank everyone for listening. And we look forward to having you back on a future webinar. Just subscribe to our email and you'll find out about it, or follow us on social media. That's a good place to find out about what we're doing. Thanks all. Take care.